Hello, everyone. Thank you all for joining the last seminar of spring term. It's a great pleasure to have Professor Peter McMahon here with us today. Peter is an assistant professor in the Department of Applied and Engineering Physics at Cornell University, and has been there since 2019. Prior to that, he completed his PhD and postdoctoral training at Stanford University. His research is focused on computing with physical systems, both in classical and quantum domain, and he has been recipient of many awards, including the Packard and Sloan Fellowships, Office of Naval Research Young Investigator Program Award, Google Quantum Research Award. He's also a CFAR Israeli Global Scholar in Quantum Information Science. So it's a great pleasure to have you here, Peter, today. Very excited to learn more about your work. Before that, I just wanted to remind everyone, if you're in the room, feel free to ask your questions throughout the talk. That's what Peter prefers. For whoever is listening to us on Zoom, please type your questions, and at the end of the talk, I'm going to help moderate the questions for you. So with that, thank you for joining, and we're excited to hear your talk.
Awesome, thank you. So thank you very much for the kind introduction, and thank you for the invitation to speak. It's a great pleasure to be here, and it's been a while since I gave a talk, and it's always wonderful to come visit. So let me start my timer to make sure that we end this on time. So my grand plan is to tell you today about computing with physical systems. So I'm going to start off by describing some challenges in modern computing that I think could be addressed by building what we think of as computing with physical systems, or physics-based or physics-inspired computing. And I'll describe a bit about how what we mean by that differs from conventional computing and how we could benefit from computing in this new way. I'll then talk about what we call physical neural networks, or how we can use almost arbitrary physical systems to perform neural network processing for us. And then I will describe an on-chip photonic neural network platform that we've recently developed that is an example of a physical neural network. And this will be towards sort of how can we scale these physics-based machines to larger and larger neural network sizes. And then finally, I'll end with some commentary on prospects or speculations about where physics computing might go. And especially since this was a nano seminar, I felt almost obliged to include some nanoelectronics in this. So we don't have any results to talk about in nanoelectronics, but I thought I'd end with some description of sort of how some of the things I talked about might be applied in the sort of either CMOS or other conventional nanoelectronic realms. So first of all, let's begin with why do we even want to build computers that are faster or more energy efficient? Maybe to this audience it's completely obvious, so I'll go relatively quickly through this, but a large motivation for us has been the growth in deep learning and neural networks. You can see in this chart here the size of or the compute cost required to train various machine learning models spanning the last several decades. And kind of if you look in the last decade, you can see this really massive increase over many orders of magnitude. And a part of the reason that this has happened is this discovery that as you scale certain neural network architectures, the more parameters you add, the more compute you add, the more capable these models become. So there's a strong sort of desire to make the models bigger and bigger. But it creates a pretty obvious problem, which is if we sort of zoom into the last decade, and we look at this nice plot of, in blue, these neural network models and how their compute demands have been increasing with time, versus the Moore's law scaling in orange of standard conventional processors, there's clearly a major issue that the models are growing, or their compute demands are growing much more rapidly than our computers have been growing. And you can make specialized chips that are designed purely for neural network processing and get some benefit from doing that. This essentially jumps the line up by a bit, but it doesn't really change the fundamental Moore's law scaling underneath it. So that is good to have, it's good to do, but it's not sufficient. Another strong motivation for us has been thinking about sensing, that there are sensors all around us, and sensor bandwidths keep increasing. So we have even now consumer electronic devices with 200 megapixel cameras. And in this example shown on the left here, if you think about some kind of a many-pixel sensor that is digitizing data at sort of maybe 50 gigasamples a second in some defense application, even if you only have 512 pixels of this, the amount of data that's coming out of this kind of sensor is enormous, 500 terabits a second. So storing that data is clearly a challenge and not a great solution to the deluge problem, but also processing it in real time is also really challenging. And something that appeared in a relatively recent SRC report is this notion that maybe one of the ways to solve this sensing challenge will be to perform analog pre-processing. So before we digitize this really high bandwidth signal that's coming into our sensor, maybe we should perform some analog pre-processing that extracts the relevant features for us. So this is something that's really inspired by neuroscience and even the human visual system, where there's really high bandwidth data coming into my eyes, but in order for me to know that the remote control is here and my mouse is here and so on, I don't need the full sort of super high megapixel resolution image. And so our brains actually do a whole bunch of processing before the information ultimately gets to the part where we make decisions. So, okay, we would like more speed or energy efficiency for both these reasons. What are some options we have to achieve that? So very generically, there's essentially 4 strategies that I'll talk about that you can try to use to make computers more, have higher throughput or greater energy efficiency. So the first is that you can eliminate abstractions. So computing is built on a great system of abstractions, which is something we all learn about in an undergraduate electrical and computer engineering degree. But it has a major challenge that now there's so many layers of this that you've introduced inefficiency at each layer. So now you could imagine stripping some of these away. For example, we rely on an abstraction of digital logic, even though it's built fundamentally on physical devices that are analog. We assume that signals are deterministic and always correct. You could imagine going towards analog or probabilistic computation. And really part of this philosophy is going to be designing behavior from the bottom up. So you start with your physical substrate and what it naturally does and build up from there rather than the conventional approach of going from the top down. And I'll have another slide on this later to give a sort of even crisper picture of what this is really all about. A second category is that a major challenge in compute systems is that your memory is often separated from your processor, and there's a bottleneck in bandwidth between the two of them, sometimes called the von Neumann bottleneck, and that you can try to address this by computing in memory. So merging the memory and compute. This is something that people, of course, already do a lot of in conventional digital and analog electronic computing, but it's a general, I think, principle that you could also apply in physics-based computing. The third option you have is something that I think, especially in the MIT.nano seminar series, many people in the audience are very well familiar with, is that you could try to go beyond CMOS. You could use alternative hardware, physical substrates, or even modalities. For example, quantum computing is something that you could try to apply in at least very specific applications. Then finally, a fourth pillar, which has for a long time been something that sort of people have been really resistant to, but is now maybe something we're forced to think about taking seriously and whether we should really do it, is being tolerant to variations. Instead of insisting that every copy that comes out of our fab works in exactly the same way for the level of works the same way we mean in our abstraction hierarchy, maybe we shouldn't insist on that anymore. Certainly, it's an option you have. If you would like to get the most out of the physical device you have, if you allow each copy to vary, you can push the performance. And so this may require some tolerating some amount of retraining or reconfiguration of the device after its fabrication. And many people have been thinking about this. Jeff Hinton had a talk at Europe's a year and a bit ago where he described this as mortal computing, that each piece of hardware will sort of fundamentally live its own life as you have to retrain it. So those are some options you have. Let's now talk a little bit about this business of eliminating abstractions. So on the left here, we see this standard stack of abstractions that you learn about throughout an EECS degree, starting from, depending on where you like, the CMOS transistors, building all the way up through insisting that they output digital logic, digital signals. You have logic gates. You can construct adders and multipliers and so on from that, building all the way up through to user applications. And a beautiful thing about this abstraction hierarchy is that if you're working at any one of these levels, you don't need to know in great detail exactly what's happening above or below you. But the price you pay for this is that now each of these abstractions is assumed to be extremely tight. And you can't just decide, oh, well, I'll make my adder only sort of add or add some of the time. That's not an acceptable thing to do in this framework where people are relying on you to do the thing you said according to the specification. A completely different way of going about things is to do what one might term physics-based computing, where we start with some physical hardware. It could be unconventional. It could just be CMOS hardware. And we treat it as a complex system that is naturally performing computations for us. And we program it by deciding on the connectivity between the components of the hardware or the parameters of the physical system that we can change. And so in this setting, the hardware connectivity and the parameters induce certain dynamics of the hardware, which in turn induce an algorithm. So you don't start at the top and say, I want this algorithm and compile down. You start with what the hardware naturally does, and you tweak it until it does the thing you desire. And so programming in this kind of model is analogous or is done by really adjusting the tunable parameters of the system. And so here there's no real separation between the notion of the program that you run and the hardware that it's running on. And this makes programming more difficult, but what you get in exchange is that all the sort of inefficiencies that you had that you were by imposing constraints at each layer in an abstraction hierarchy are now all gone. So I wanted to give one example of this kind of physics-based computing modality that's been explored over the last decade, and that including by people at MIT. So maybe some of you will have seen this before. If you have, great. If you haven't, you can ignore it. We were not going to use it later in the talk, but I wanted to give at least one example for those of you who are familiar with things called icing machines. So icing machines are special purpose pieces of physical hardware that have been designed to, through their natural dynamics, heuristically perform combinatorial optimization. And an example of this is something called oscillator icing machines, where people have proposed connecting nonlinear oscillators. For example, it could be like a nonlinear capacitor and an inductor that are coupled, for example, resistively, as shown in this example, to another spin. And the idea is that you would design these through their natural dynamics will naturally minimize an overall cost function given by an icing Hamiltonian. And this is something that's now been sort of even scaled up relatively large. This is an example of 2,000 oscillators in a CMOS device. And in this kind of setting, you have essentially a network of coupled oscillators. They have some dynamics. This is describing the evolution of the phase of each oscillator. And really, the thing that gets programmed here, there's no program. The thing that gets programmed is how is each oscillator coupled to each other one, which is this Jij in this formula here. Another example of this is probabilistic bit machines, where people have taken stochastic magnetic tunnel junctions, which behave as essentially probabilistic bits that you can bias, connected them together in networks. They have a slightly different dynamics than these oscillator versions, but a very similar concept holds. So you essentially, the system is doing what it naturally does. These SMTJs are sort of flipping back and forth, and the thing you control is how they are connected. And there's been work at MIT and Dirk and Marin's group and also Luchao's group on this kind of thing. So some of you might have seen this before. So this is an example of what I mean of getting rid of the abstractions and really just working at the base level of the physics. So now the first story I want to tell you about is work in our group on constructing neural networks in this kind of way, of taking physical systems and operating at the level of the physics to construct or perform neural network inference. So some sort of quick preliminaries, and mostly so that I can show you some diagrams so that you can sort of match them to diagrams later on, is if we think about a deep neural network, really what we mean by deep is that there are multiple layers. So here is an example where we have some image encoded in a vector. Let's have this dog here. And this data gets, or this information gets propagated through multiple layers of a neural network, where we can think of each of these sort of boxes here. There's supposed to be a gray box around it, but it's okay. Or a single layer of the neural network that performs some function on the input vector and outputs another vector. And this gets propagated through until out pops the answer that, okay, this thing that you sent in was an image of a dog. really, the way we like to think about this is that it's a network or a composition of functions. You're taking an input of a dog and some parameters that control what function is implemented here. You compute it, and then you're passing it to the next one, so you're now sending that as an input to the next function, and so on and so on. So really, this is a specific ansatz for a function that takes an input and a set of parameters and produces an output. And of course, okay, if you put a cat in, you should, if your network is trained correctly and these parameters are set right, it should predict that that it's a cat. So how does this training happen? Well, if we start with a network where the parameters are just set randomly or untrained in some way, then you'll just get a random answer out. And training proceeds by updating the parameters so that when you put a dog in and it gives the wrong answer, you maybe prod the parameters and move them in a different direction. And then once you've fixed these parameters for all of these layers here, now you can perform inference, where you can put in a new image of unseen data and have it correctly make a prediction. And so everything I'm going to tell you about in this talk today is really going to be about making hardware that could potentially be more energy efficient or faster for the inference task. But by necessity, we have to have done training to get there. So I'm not going to give you a method to improve the speed or energy efficiency of training, but I have to cover it in some way because otherwise I couldn't have gotten to the inference phase. And this is sort of not a silly thing to be doing. Even if you only solve the inference problem, already that's a very large fraction of cloud compute for machine learning, because you train a model once and then sort of, at this point, literally hundreds of millions of people may use that model in inference mode. So how are neural networks implemented in conventional hardware? Well, if we think about a typical layer, the sort of most simple form of this will be, this layer of a neural network will be performed by a matrix vector multiplication. So we have a vector in, we get a vector out, and they're related by a matrix vector multiplication of what's often called the weight matrix W, describing the connections between the neurons and the input vector. And then at each point, or each neuron, each element of the vector, an element-wise nonlinearity is typically applied, something like this ReLU function. And this has been implemented in hardware accelerators and digital electronics, where you have things like systolic arrays, where you can almost see like the spatial structure of the matrix in the hardware itself, if you squint. And people have also been working on analog processors in electronics. For example, this crossbar array here, where you send in the vector as voltages on these blue lines, and then they are connected to the red lines via programmable resistors, so memristive devices, or resistive memory devices. So the weight matrix is encoded in these elements that connect the wires of the crossbar, and then you read out your answer as currents on the red lines. And this here, you can really see that like the hardware has been designed to perform this matrix vector multiplication. And people work really hard at getting these kind of devices to exactly perform a matrix vector multiplication. So we ask the question of, do you really need to do this? Do you really need to make matrix vector multipliers to do neural network processing? I mean, intuitively, the answer should be no. Like, I don't think what's going on inside here is a high-precision matrix vector multiplier. But can we try show this with a sort of less exotic hardware than the human brain? So what we're really going to do is say, okay, currently the mode people work in is they run some Python where they call ReLU on a matrix vector multiplication, and that gets compiled all the way down. We're going to see if we can instead start with some hardware and build up to it performing neural network inference. And let's not take something that like almost does a matrix vector multiplication just a little bit off. Let's really see if we sort of make no effort at all to make the physical hardware perform something that we recognize as being like a neural network computation, and see if we can succeed. So the training in deep learning, or deep learning is really just about training these controllable functions. So if I'm trying to classify this MNIST handwritten digit 8 here, we're really just about trying to pick parameter values, theta 1, theta 2, theta 3, where each of these are vectors, such that when you put it at 8, you get out the correct classification. So it's just about tuning the parameters so that it makes the correct prediction. Another observation you can make is that every physical system, or almost every physical system, really is, you can also think about as performing a controllable function. So the quantum.tv is broken, and over here there should be a gray box. For those of you on Zoom, you will see it. But for those of you in the room, the gray box is invisible. But imagine there's a gray box here that represents a physical system. And if you have some control over how the physical system behaves, you have some things you can control about it, and then there's things you can measure about the system. You can think about this, the undergoing time dynamics of some physical system as just having the physical system perform a computer function for you. It takes in some input, and it performs some function according to its dynamics. You can kind of arbitrarily split the things you can control about the system into what we might call the data, input data, and what we might call parameters. This is a sort of arbitrary distinction that you're allowed to make. And so you can then think about any physical system as really performing controllable or trainable functions for you. So what's an example of a physical system that performs some physical function for us and then controllable function? Well, this is a somewhat exotic example constructed in optics, but maybe a strong benefit of it is it clearly doesn't look like sort of conventional neural network hardware. We have at the heart a nonlinear crystal that will perform some frequency generation, and since this isn't an optics seminar, I won't go into great detail about the optical physics that happens here, but suffice to say, essentially, you can think about this box as being able to take sort of two photons and add their wavelength, and you get out a photon of a higher energy. Oh, sorry, add their energies, and you get out a photon of a higher energy. And we're using this in a setting where we shape the spectrum of the pulse that gets sent into this nonlinear crystal with a pulse shaper, and then we measure the spectrum out with a spectrometer. So if I feed in a light with frequency omega 1, what comes out is light at 2 times omega 1. If I send in light at omega 2, then we get light out at 2 omega 2, because you've just added 2 omega 2 photons together. And if you put in light of 2 different wavelengths, you get this sum coming out of omega 1 plus omega 2. Now we can imagine putting in an input spectrum that's a bit more complicated than just 1 or 2 single frequencies, that it has this spectrum here, and we can look at what we get out. And you can see that what you get out is actually at least a non-trivial by eye mapping of the input. And you could think about dividing some part of this spectrum on the left that you input as being, you can denote some part of it like this part that's increasing in the animation as the part that's going to control what function this thing realizes. So you could now really think about this optical system as realizing a controllable function of your input light. So the next, or the key idea then is, given that physical systems realize controllable functions for you, is you can then take your standard sort of neural network diagram and think, well, what happens if you take this block, this layer of the neural network, and replace it with a physical system that that computes a physical function for you? And in fact, you could do the same thing on a deep network. You could take sort of each layer and replace it with, imagine there are gray boxes where there are holes here, with copies of this physical system. And each one can have different trainable parameters, and this thing will then realize some complex, trainable physical calculation. So we did this with this nonlinear optical setup that I showed you a few slides ago, where, well, we didn't copy the entire setup 5 times, but we used it 5 times in a sort of time multiplexing fashion, where again the gray boxes here are missing, but imagine each of these gray boxes is a copy of this, conceptually a copy of this frequency conversion setup. And then each layer is going to have different set of parameters, and what we chose to be the parameters was the left-hand part of the spectrum. So we just declared, we can arbitrarily do it, declared that the left-hand part of the spectrum, those are going to be the tunable parameters, and then the right-hand part of the spectrum is going to be the input data of what we're trying to classify. And we did a demonstration of this for classifying spoken vowels that have been then encoded in what the people in this community call formant frequencies. And the idea is that at the end of sending this signal through the network, if we look at the spectrum, the part of the spectrum that is the highest intensity, that will encode which vowel it's being classified as. So the key part of this then is, how do we train this? How do we figure out what parameters, so what values of the spectrum we should put in at each layer of the network? And the sort of two key ideas for how to do this was, first, let's use a differentiable digital model of the system in training. So a laptop is going to be involved in training, not in inference, but in training, so that you can perform gradient descent using backprop, which is sort of a great algorithm for training these things for we know all the reasons we know and love, especially the fact that in a single pass you get back a gradient. So you get back all of the derivative with respect to every parameter in a single pass. And the second key idea to make this work is really you don't want to do everything in the laptop. You only want to do half the work in the laptop. You want to do backward passes in the laptop, and you want to actually use your physical hardware to make predictions that are going to be used to compute your loss function. So let's see if I can get out of the pointer mode and play a little video. And then somehow move this. Where's my pointer? There we go. And so we'll see this now. We have some choice of parameters and data. We send it through the physical system. We get an answer that's not quite correct. So we were supposed to be classifying this as an 8, and it was not. We compute an error, so how far off was the prediction? You send that error through the digital model on your laptop, and it computes a gradient. And now you can update your parameters and then sort of repeat this in a cycle. All right. So when we do this, sorry, let me get my mouse pointer back. So when we do this, as a function of epoch, so how many times we've been through the training data set, we can look at the accuracy of classifying the vowels, which was the task we were trying to do. And we can see in the blue line that as you go through the training set, you manage to get up to 93% accuracy doing it in this way. So this works. The black line is what we got the first time we tried this, when we didn't do it in this sort of hybrid manner of forward pass through physical system, backward pass through digital model, where we only did the training in a laptop. So forward pass and backward pass both through a digital model. And it doesn't work well at all. And the reason for this is that our model of the dynamics of the physical hardware is a little bit inaccurate, because modeling analog systems with great quantitative accuracy is really difficult. So that doesn't work well. But once you introduce this sort of hybrid scheme, then it works really well. And the intuition there is, so long as your differentiable digital model is accurate enough that it gives you the signs of the gradient correctly, then you at least make progress and you move in the correct direction. So we also did this, we also tested this algorithm for training on a few different physical systems, and with the task of handwritten digit recognition, which is a little bit more difficult than vowels. We managed to do it with a mechanical setup of a piece of metal that was shaken, which is also kind of a weird physical setting. Question?
I had a question on the previous slide. So I assume that going from the error to actually updating the parameters is not trivial. Is that correct?
It wouldn't be trivial if somebody hadn't already written PyTorch for us. But we are literally building or standing on the shoulders of giants. And so we can literally use all the machinery of backprop in something like PyTorch to do that for us. So we compute the loss function, so this error, and then we need this differential. The thing that's not in PyTorch by default is, what is the differentiable digital model of our physical system? That we had to come up with ourselves. But once we have that, then we can sort of chug through. And I think this would have indeed have been like a couple of years' effort in the, I don't know, maybe early 90s. But now it's easy. Question?
For the input parameters, are they like just literally one for one? Oh, sorry. Input parameters, are they one for one? It looks like half of your spectrum, or what it is your weights, and the other half is your input parameters. Are you able to just set the input parameters 1 to 1 once you've completed the training, or do they also need like a slight mapping?
Right. Essentially, the answer is they map 1 to 1. I mean, there's like an implicit thing going on though of like, how do we set that part of the spectrum? It's like, well, we get to update values in a lookup table for a spatial light modulator. And those are really the things we're changing. And so it's like, we're not directly changing the spectrum. We're changing the thing we can control of the electronic device that changes the spectrum. But yeah, there's no like extra trained thing to go from trained parameters to inference parameters.
Thank you.
A follow-up question. So your inference. Thank you. Do you also have many different layers, and each layer is the same crystal but with a different shaper and output?
Great question, yes. So the short answer is yes, we have many layers, both in inference and in training. And in training, just so that I didn't have to draw this thing with many layers, I already showed one, but it extends naturally. Also, great thanks to PyTorch. So yeah, we're doing this vowels example we're doing with 5 layers, and then some of the other examples I'll show, we had slightly different architectures with varying numbers of layers, but all of them with more than one.
I see. So for each reference inference, then for each layer, when it propagates to the next layer, how do you implement it so that it's not blocked by the manual tuning speed of a graduate student?
Right. So it's not blocked by the manual tuning speed of a grad student, but it is currently bottlenecked by something else, which is also not desirable. We'd like to get beyond it, which is in this optical setup, for example, we measure at the spectrometer, but then how does that get fed to the next layer? It's like, well, it's now in electronics, it's in some laptop, and then we feed it into the sort of data for the pulse shaper for the next round. So there's some limit on the throughput of the system of like how quickly can we take the output of a spectrometer and feed it into the pulse shaper for encoding the data for the next set, which we'd like to get rid of, but it's a limitation of the current sort of paradigm. So I think as we think about sort of, incidentally, none of the examples I'm going to show you what I'm saying you should build a neural network like. These were more sort of chosen as extreme examples of like, you can do it this way. We would like to think about sort of how do we get rid of these bottlenecks. But fortunately, it was not limited by how quickly somebody can type on a laptop or anything like that.
So the function f sub p needs to have certain mathematical properties. I'm not sure they need to do some kind of integration. And it looks like you do that here because you're converting things to spectra. But can you perhaps go into just, have you characterized the kinds of functions that are even, that are possible by some of the physical means? Because I don't see how, not everything's going to do this, right?
Right.
Not every physical system is going to nicely behave like this.
Right. Yeah, it's a great question. So a sort of pithy answer is, I told you that pretty much every controllable physical system can be used to do neural network inference. I didn't promise you that it would be good, or good at it. So, which is maybe a little glib, but it's actually pretty close to the truth. It's just like pretty much any neural network architecture you could come up with in a Neural Networks 101 class as a homework exercise will act as a neural network to some extent, but whether it's good or not, well, that's an art. So that's part of it, is figuring out what, and it's task dependent. Some architectures are good for some tasks and not for others. So that's part of the story, is finding physical hardware that matches the task well and does have the sufficient sort of complexity. But I think there's a really sort of even deeper thing that's really interesting there, which is physical systems, we can think about what mathematical function they implement just from sort of analyzing it from a physics perspective. And often when you're doing things, you'll naturally see a convolution arises in how the inputs and outputs are connected. And you can have some intuition from the computer science side that convolutions get used in, for example, image processing in the earlier layers. So a system that naturally performs convolutions might be good for that. But we also know that sort of highly connected systems are good. So if you give me some system that are very sparsely connected components, that's probably not going to be very good for most tasks. You want something that with sort of all of the internal elements, the neurons, if you will, sort of speak with each other a lot, but also that connectivity is programmable. And we're still just beginning to learn sort of what intuitions can we take and then how do we realize them in different physical systems. All right, great. So I wanted to give another couple of examples of demos we did with this, but I also want to move on to talking about things that are sort of less toy examples than these ones. So just going through relatively quickly, we did an example with mechanics, which was also picked not because I think you should make your neural networks and replace GPUs with mechanics, but because it's an example of something that you would naively maybe not expect to be able to do handwritten digit recognition, and yet is able to succeed, at least to the level of about 90% accuracy. So this is literally, we have a piece of metal that we shake with an audio speaker, and we listen to it with a microphone that's sitting up there. We also did one with the world's simplest analog electronic neural network. It's an RLC oscillator where we added one transistor, again for the intuition from CS that nonlinearity is very important in giving sort of power to neural networks. And this does a little bit better. And then we also did a demo with the optics setup that I already showed you. So something that sort of naturally comes up with this is like, well, okay, first of all, you did some toy demos. Can you do better than you did if you get more sophisticated hardware? And then how tolerant is this whole thing to sort of variations from hardware and mismatch between the model you use in the training and the actual inference? So we did some simulations with a prototypical model of coupled oscillators with 1,000 oscillators, which is larger than the hardware we had, but it's something that sort of shows how does this scale. And for an easy task of MNIST handwritten digit classification, we can then get to state-of-the-art accuracy with a network of 1,000 oscillators. So this is now solving the MNIST task a completely different way than a sort of neural networks 101 would do it, but it's also possible in this sort of weird paradigm of like connected coupled oscillators. We also tried a more difficult task, which by ML standards is not actually hard, it's just hard for us in this sort of nascent community of fashion MNIST, which is a variation of image recognition of garments. So like, is it a t-shirt or is it trousers or whatever? And we were able to show that we can train these network of 1,000 oscillators or 1,000-ish oscillators to perform MNIST fashion recognition accurately. But then we can also sort of see how do we, if we make our model and our simulated hardware mismatch, how much can we tolerate? And it turns out that with this sort of physics-aware training type approach, you can tolerate a mismatch of up to 70% difference in the parameters of the model versus the actual hardware and still have it perform inference at a almost state-of-the-art level. And similarly, you can train it to be in a way that it's resilient to variations from device to device. So you get a new device off the production line, it's up to, let's say, the parameters of the components are 10% different from the ones you trained on. So long as you've trained it in this style, if you just transfer the parameters to the new device, you'll get almost the same accuracy, so 87.5 versus 88.9. So the main kind of things we take away from all this work so far is that we can make functioning neural networks out of physical hardware without forcing the hardware to do sort of very specific mathematical operations. We've given a training procedure. I won't say that it's the only training procedure or the best training procedure, but it's a way that we were able to train these things. And the system doesn't need to be noise-free to work well, given that I showed you experimental results that took place in a real lab. That's hopefully convincing. And we, of course, also have the simulations that sort of back up about how that works as it scales. And yeah, you can work with pretty imperfectly calibrated hardware, and this transfer is possible. So this sort of covers, well, it's feasible to do this. It's general across a fairly wide variety of devices. The training is efficient because we use backprop. And these things look like they could be they're manufacturable because you can tolerate these variations. So now I want to tell you about some work we've done over the last year or two that recently came out as a preprint that is on a specific photonic realization where we look to scale up photonic neural network, on-chip photonic neural networks using this sort of style of thinking about things. So many of you may know already, there's a large effort in on-chip photonic neural networks that was really pioneered here. This paper is from Dirk England and Marin Soljić's groups from 7 years ago now, where they performed matrix vector multiplication on an input vector of dimension 4 to an output vector of dimension 4 using an array of Mach-Zehnder interferometers. And in the sort of intervening 7 years, people have been pushing the scale of this, but they found it really, really difficult. So if we look at the state of the art in input vector dimension and output vector dimension, this original work was there, and sort of some people have managed to push up a little bit and push a little bit on the side, but it's nowhere near as big as we would like. And no one ever shows you a plot like that without sooner or later in the presentation we're going to fill in a new point in this plane somewhere. And we really tried to be fair in this plot, though. This is including many of the sort of most, or as far as we know, all of the main recent results in this field. So we'd like to scale these, but it's proven really difficult. And part of there's many reasons for it. Part of something to notice here is the scale bar. That these MZI devices are not that small. It's 60 microns in the scale bar there. So a really interesting idea was proposed in 2019 from Shanghai Fan's group at Stanford and one of his former students, Zhongfu Yu at Wisconsin. They both simultaneously proposed this idea of if instead of we make a mesh of MZIs or a crossbar or phase change memories or one of the many other approaches people have taken to building on-chip neural networks, what happens if you give me a slab of material and you just let me program the refractive index of it arbitrarily? You'll get these sort of very weird patterns that control the light in weird ways, but you can train it to do inference. It was a really fascinating idea, but they left open a major question, which is they showed that in simulation this will work, but they didn't say how you could make a device whose refractive index you can control as a function of space. So how can you do that? How can you make a device that's like a slab waveguide shown here, where you can control this map of refractive index? And that's what we set out to do. So we recently worked on this and did an experimental demonstration where we at least provide our solution to this problem. There are other people working on it as well. But our solution is as following. So we start with a silicon substrate, and we add a slab waveguide. Ooh, we're going to go back to like having missing boxes again, which should be interesting. But the most important part here is the red bit, which is a slab lithium niobate waveguide surrounded by cladding. So that's where the light is going to, that we're trying to do computation on, is going to propagate. And then we're going to add a big chunk of photoconductor on top of that, and then an electrode. And we want the electrode because we're going to bias this with the voltage. And why does this let us control the refractive index of this red waveguide as a function of space? Essentially, the answer is we're going to use the electro-optic effect in the lithium niobate, but in a slightly weird way, that if we look at a patch of this device and we sort of go down taking a cross-section of it, what we see is that effectively we have a circuit model where we have some resistance, or really it's impedance, but you can think about it as resistance of the photoconductor and the resistance of the waveguide. And so there's a resistive divider effect for this bias voltage that's put on. About half the voltage is going to drop over the photoconductor, and half of it is going to drop over the lithium niobate waveguide, which we will define as that having no refractive index contrast. Now you just sort of get this extra phase shift everywhere in the waveguide. Now, imagine you shine light onto this waveguide from above with a pattern. And this pattern is going to be directly transduced into a refractive index pattern. And the way it works is that wherever you have, like for example, this region here that we've sort of done this inset to, wherever you have light, the photoconductor will absorb the light by definition. It will increase its conductance or reduce its resistance. And now your resistive divider will have a smaller resistor for the photoconductor part, and so you'll drop more of the voltage over the waveguide, and through the electro-optic effect, you will now induce a phase shift at that part of the waveguide. In the work that we're presenting, we've achieved a refractive index contrast of 10 to the minus 3. We think it should be possible to push this to 10 to the minus 2. This is enough that we can do an experiment like this where we shine the pattern. This is literally a pattern that we shine, like an image, onto the top of our chip. And we pattern this sort of pattern of this fork shape, and we send in a beam in the middle, and what we see come out, this is experimental data, we see two beams coming out. So this is showing that you can effectively make like a beam splitter device in this way. So this is showing that the physical mechanism is working. This shows a picture of our chip, and we're shining this pattern from above. You can see sort of the pattern here. It's like below eye resolution, but you can see the green light at least. So the green light is what we're sending into the photoconductor. Then we have infrared light coming in and out as the light that the computation is being performed on. you can imagine using this platform, not just to make beam splitters or other programmable circuits, which is indeed something you could do, but you could use it to perform machine learning in the same sort of sense as the MZI array chips, where we're now going to have this pattern that is going to encode our parameters of our neural network, and we're going to perform a gradient descent update of those parameters using the physics-aware training sort of hybrid loop that I showed you in the last section. So you could imagine encoding an image into the input vector. You have to do some sort of unfolding to get it into 1D, and then trade it so that when you get the output that it's sort of peaked at 2 because you put in an image of 2. And this is really happening through this physics of wave propagation through the waveguide, where the sort of refractive index modulations are the things that are changing how the waves from different input digits are being changed. So if you put in a different digit, you should get a different pattern of wave propagation coming out. So we tested this on MNIST handwritten digits with a variation, so not the full size images, but 7x7 downsamplings, which makes the task harder. It's more difficult to identify the image when you shrink it. And we feed it into the system by just sort of reshaping this array to 1D. So it's a 49-dimensional input and a 10-dimensional output because we're just trying to classify in a single layer what image we had. And we achieved an accuracy in experiment of 86%. And that puts us over here. So we're not anywhere near what a GPU can do. It's not by many, many orders of magnitude. But we've really managed to push how big the computation is that the on-chip platform can do in these spatially multiplexed examples. And this is really in large part enabled by the fact that we sort of got rid of the abstraction of these discrete components and just directly programmed the physics. So yeah, so what sort of principles of this did we use in this example? Well, we didn't insist on exactly performing a very specific matrix vector multiplication. We just sort of trained on the parameters that we could control. We are doing in-memory compute. The parameters are sort of sitting in the waveguide, so to speak. And it's using an alternative hardware. It's using photonics. And we trained on a specific device. So we're tolerant to the fact that the devices that come out of our clean room that the student and postdoc who built this make is a little different each time, but that's okay. We have a training procedure that can handle that. So now in the last, let's say, 5 minutes or so, I'd like to talk about some prospects for where I see this general field, so to speak, going. The main things I'd like to touch on are a near-term application. So clearly, building a system that can beat a GPU at running ChatGPT is extremely difficult, and we're not going to do that anytime soon. So what can we do in the interim? So I think smart sensors are a really good answer to that. I'll also talk a little bit about how we might imagine building large-scale neural network accelerators that connects with the nano theme of this seminar, and then I'll say a couple of words about possible extensions to quantum neural networks. So smart sensors are this notion of you can have a sensor that is integrated with a neural network that sort of pre-processes the data, and this kind of physics-based or physical computing paradigm is very well suited to this because you may have many different things that you're trying to sense that are not electronic. They could be photons, i.e. optics. They could be sort of acoustic waves or mechanical forces, etc. And a natural paradigm for pre-processing this is first make an invisible gray box that has a physical system that is the same modality as this. So if it's photons, then you should have some optical system that pre-processes to extract the relevant information before you transduce, digitize, and then do further processing. And as one example of this, we recently, or not recently, I guess the paper came out about a year ago now, did an example where we used a 2-layer optical neural network to extract the relevant features of a 3D printed scene where we have a traffic sign and we're trying to extract what is the speed limit on that sign. You don't care about all the sort of great details of this image. You just care about what are the numbers on this sign. And we were able to achieve a compression ratio of 400 to 1, where you can digitize just 4 pixels and are then able to accurately classify what the speed limit is. So this is an example of sort of doing this pre-processing. You're not doing the full thing in the physical system, but you're greatly reducing the bandwidth that you have to digitize and post-process by doing this sort of pre-processing in the analog domain. You could imagine playing the same game with microwaves. It's not specific to optics, and that's something we're working on with a mixed signal CMOS group, where sort of heuristically you can think about like wideband radar having 100 gigahertz of bandwidth. It's a little bit weird that you have to digitize 200 gigasamples a second in order to tell very few number of bits. So like, what airplane is it and how fast is it moving? It feels like a natural place where you can sort of benefit from trying to pre-process in the analog domain. We're also really interested in, even though it's really difficult, how you can make analog electronic neural network processors that might ultimately actually be able to beat GPUs at running ChatGPT. It's really, really challenging, but we're inspired by the fact that the human brain has a vastly larger number of neurons and parameters, synapses, than artificial neural networks, and yet only uses 12 watts of power. So it feels like, in principle, we should be able to do much better than we're currently doing now. And so there's a bunch of strategies you can take, many of which are not kind of unique to us. People have been thinking about these for a long time, of like lower the voltage, operated analog. You can think about tolerating noisy components, maybe using exotic hardware, et cetera. Something that I think is actually an idea that is really interesting, but that is something that people have kind of ignored for a long time, is the notion that you don't need updatable memory anymore. And this is something that's a bit new in the last 5 years. 5 years ago, if you wanted a neural network accelerator, it's almost by definition that you must be able to change what neural network it runs, because you want your chip to be able to do many different things. But this has changed. Now that we have what people are often calling foundation models, things like GPT, where it's trained on the entirety of the internet, and OpenAI brings out a new GPT model only every 1 to 2 years, and that model can do many different tasks, and you can sort of post-tweak to do many different tasks. It's maybe not so stupid to think about, can you or should you make a neural network accelerator that's sort of printed? It's like a CD-ROM, you print it, that has the latest model on it, and you use it for a year or two, and then you throw it out and you buy a new one when the next model comes out. And if you do that, if you don't need programmable memory anymore, that is greatly reducing a constraint on your engineering. So you can maybe get large factors of benefit in both speed and energy by having sort of printed, prefabricated neural networks. So a couple of ideas for sort of just concepts of how one might benefit from this idea. One is people have built these crossbar arrays where they use memristive devices, but the transistors that you use to drive the currents to update the weights are actually pretty large, and so the unit cell sizes are pretty large. And people are also insisting that this thing do exactly a matrix vector multiplication. You can maybe relax both those assumptions and then shrink the unit cell size. And there's probably potential for sort of a few orders of magnitude win from doing that. Another kind of even more exotic idea is to maybe try and make some nanoelectronic material where you pattern the material in 3D or 2D space. And if you just sort of do a counting argument of like how many voxels you have when you pattern the conductivity of a 2D, 3D material versus some sort of reasonable size of it, you can imagine really getting a very, very large number of parameters embedded in your system, but they're fixed. But that may be okay. So one concrete idea for how to maybe try something like this in the near term is imagine taking a slab of silicon and then patterning the P and N type dopants in a completely programmable way. And if this diagram looks a little bit familiar, we were inspired to do this by the work at the photonics side. Like, can we take the photonic reprogrammable refractive index idea and do the same kind of thing in nanoelectronics? I think the answer is yes. I have a new postdoc who will be starting working on this in a couple of months, and so we'll sort of check back in this space in a couple of years, and we'll see if we succeeded. But I'm really, really excited about this direction. I think there's lots of different ways you could try and do it. I will say epsilon about quantum neural networks, which is a very natural thought for at least someone from my background, or I came from the quantum optics background, quantum information background, is can you play the same game with quantum physical systems? Everything I've told you about so far are classical, but we have the same story in quantumness of people are thinking about sort of many layers of abstraction to build up fault tolerance and universal quantum computing. But if you want to get sort of wins in the near term, maybe it makes sense to play this game of try to do the same thing we've done in classic, of like replace the physical system with maybe some dissipative, maybe poorly calibrated quantum system, and then try train it in this way. And maybe there's an interesting question of like, well, what should the equivalent of the laptop be for training a quantum system in this way? Maybe it should be a standard circuit model quantum computer. Maybe it can be some sort of like approximation of the dynamics with like some tensor network approximation. We're still busy figuring this out. This is something we're actively working on, primarily in the superconducting circuits domain. So with that, I should acknowledge the group and everybody who did the work, as well as the people who are funding this work. And I'll leave you with some thoughts of, we've shown that you can make physical neural networks and harness the natural dynamics of many systems. In our on-chip photonic neural network scheme, we've sort of proposed this new way to make a programmable refractive index as a function of space. And this seems to be an interesting way to sort of push the scaling of these on-chip devices. And then sort of thinking towards the future, I think in-sensor or smart sensor processing is a really promising near-term application. But photonic neural networks and nanoelectronic neural networks should be competitive if you can make them large enough. And so a big challenge is how are we going to really be able to scale this? That's something I'm looking forward to working on for the next few years. I think it should keep us busy. So thank you all so much for your attention. Thank you for the questions that we've already had, and I look forward to more questions and more discussion after the formal end of the talk.
Okay, we'll take a few questions, but just a reminder, there is going to be a reception right after, so for now we'll take a couple questions.
Hey, Peter. Thanks for the great talk. So I find the need for the differential digital model to be like, I don't know, it's just kind of unsatisfying. So I'm wondering if there's a way you can use the physics of the system to get that differentiability, like using Lorentz reciprocity and the response to perturbation. I don't know. I'd just be interested in that.
It disturbs us too. We would really like to get rid of the laptop because, for one thing, it means that we have no chance of getting a speed or energy boost in training, and we would like to be able to do that. So there's a bunch of people thinking about a bunch of different ways, and in the optics case, Alex Lvovsky's group at Oxford, for example, has this interesting proposal for a very specific setting. If they send the light through in one way, it does the forward pass, then they can compute the error, and if they literally send it backwards, they can engineer, they can engineer it so that you get gradients. But it's a very specific setting, and like the largest demo they've managed to do is I think like something like with 2 layers of 3 neurons or something like this. So it's really hard. The engineering is difficult, but it would be really nice if you could make something like that, but generalizable and tolerant to variations. Florian Marquardt's had a few really interesting ideas in this space as well. Yoshua Bengio's group brought out this notion of something called equilibrium propagation for any system that equilibrates. Their theory roughly holds, and that's also sort of a local rule where you don't have to run backprop on a laptop. So there's a bunch of ideas, but nobody's yet sort of stumbled upon like the one thing that's clearly going to be the winner. Our PAT method, I literally described it as like, it's a way to do it. I certainly wouldn't say it's the best or the end. I hope it's not the end.
Great, thank you.
Thanks for the talk, Peter. It's hard not to listen and wonder about applications in control. So maybe you could comment a little bit on that.
Right, yeah. I think there's this sort of nice merger of sort of traditional control community and reinforcement learning community. And this kind of stuff naturally plays in with that because, okay, once you allow yourself to do reinforcement learning, you can naturally imagine a physical controller doing the reinforcement learning. And this feels really interesting for sort of very small scale systems where you're very constrained in the amount of power you have. That said, I dug into it a little bit in the case of sort of micro robots because I had the same thought. I was like, maybe these people who are building sort of really tiny robots could use this. But it seems really challenging because they can already get the CMOS processors that do the control down to like an amazingly small size and power budget. And so after speaking to a few of them for a little bit, I became a little bit less optimistic that there's like an easy win there. But it really does feel like ultimately you should be able to benefit. It's just, already the CMOS has already gone there. And once that's happened, it gets really difficult to win.
Yeah, and again, very nice talk. Sort of coming from a similar space with the sort of pre-compression algorithms that you guys are implementing physically, do you guys foresee those needing to be reprogrammable? I mean, how do you decide, and especially like an autonomous system, if you're trying to pre-compress sensor data, along which dimensions to compress and when those scenarios are appropriate, and then how do you then in turn, keep your system from being too generalized? How does this sort of adaptability between very compressed and not compressed at all come in?
Right. Yeah, so I think the way we think about it is largely like take any, like for example, machine vision system that is already using deep learning to make inferences from the images. This is a natural setting to immediately do that. How generalized should it be? It's like, well, how generalized are they currently doing it? How wide is their training data set, so to speak? You can just do literally exactly the same thing, but now you're going to reduce a bottleneck in the middle. If you want to go to new applications where people aren't already doing machine vision with deep neural networks, then you have much more thinking to do, but it's not really thinking that's specific to our way of doing stuff. It's the same questions you always ask when you say, is it okay to use machine learning to do X? And how much training data do you need? How much do you need to update it? How often do you need to refresh it? That's true of anyone even doing it the conventional way. Our way just gets rid of the bottleneck.
Thanks for a nice talk. So for restricted Boltzmann machines, there's this kind of bipartite connectivity that my understanding is they use to be able to use backpropagation and kind of training. Do you have similar restrictions on both kind of the physical systems? Again, I guess this is another way of asking the same question that's been asked a couple of times already, or physical systems or training mechanisms that you would use to enable this backpropagation training for your system? Like, are there classes of systems that work better or worse than others?
The key thing for us for trainability is really how good is our differentiable digital model. So you don't need to necessarily restrict the system to be in, like taking on some bipartite graph like in RBMs, but it's a pretty general statement that you want your model to be good enough that the gradients have the correct sign. And certainly you can imagine some constraints on the hardware to let it not go into regimes that are too hard to model. So that's one constraint. Like for example, I'll sort of thumbsuck an example. It's not like a real example, but imagine in our 2D waveguide stuff that if we pumped so hard that the lithium niobate started doing frequency conversion, now our model of the wave propagation, if we didn't model that part, would be off, and so things wouldn't work well. So you'd be like, well, you should restrict yourself to low enough powers that doesn't happen. Is an example, but there's many settings in which it helps you at least to be a little bit constrained so that your model is good.
Thank you.
Thanks for the talk. I had a question about kind of how many layers you can embed within these physical systems. I think most of the examples you showed, there's kind of only one set of weights and one physical system that you're tuning. Have you tried sending your model through multiple sets of physical systems, and do you see any change to your output there?
Right. So this one here, the first set of examples I showed of vowel classification was actually with, I think, a 5-layer neural network. So we had 5 conceptually copies of the nonlinear optical crystal. Like in practice, we actually, the lasers are expensive, so we only had one, and we send it through, we measure the data, then we send through another and another, we multiplex it in time. But certainly what's happening from a computation perspective is a deep computation as you go through these 5 layers. In some, it depends on the example. Like in the sensing example that I told you only for about 30 seconds, but there were two layers in the reprogrammable waveguide. We actually only did 1 layer, not because we couldn't do 2 or 5 or more layers, but because we wanted to demonstrate that even with just 1 layer, we can actually get close to the sort of theoretical maximum for a linear classification.
Thanks.
Maybe one last question, and then we'll open it to the reception.
Hi, thank you for the interesting talk. I'm curious, in the physical neural network examples you give, you still kind of keep this layer-wise structure, whereas I guess if you have some parameterizable physical system, you should be able to just tune those parameters themselves without the use for layers. Like layers doesn't feel like a fundamental design choice. I'm curious, what are your thoughts on, I guess, maybe that's like an optimization problem, or generally like how learning could or should work, alternatives to backprop, that sort of thing.
Right, right. Yeah, that's a great question. So one sufficiently complex physical system should be able to realize something that is effectively a deep computation. So in principle, I should have been able to give all my examples with just one physical system. I shouldn't need multiple. But engineering one system that does the sort of the whole thing you want is actually kind of challenging. It goes back to the question that we were talking about a little earlier of like, what does the physical system need to be able to do? If you wanted to do, I don't know, maybe it's getting a little too close to like following exactly what CS people do, but like a convolutional neural network with convolutional layers followed by fully connected layers. If you want one system that does sort of everything, you can imagine that it's pretty natural to actually have two different ones that each sort of do the different part better, rather than trying to engineer this one that in principle you could make, but what physical system is that? That said, this kind of idea here, I'm kind of optimistic that actually if you give me a big enough piece of silicon, like you can actually get this thing to learn the whole thing all at once. It's probably going to be a really hard trading problem though.
Great. So let's thank Peter again for a great talk.
Thank you very much.
And thank you all for joining. There's going to be a reception, so please stay back. Peter will also be here so you can chat.